Hello, this is Soham Bapat, and I am making a presentation on the homework 5. So this is the problem statement. You are given a string ti, n of n characters from a constant sized alphabet, and we want to find the longest substring of t appearing at least twice. This is similar to the longest common substring problem. But in this case, we are trying to find the longest substring in the same word that is appearing twice. So we know that this can be solved using dynamic programming that requires quadratic time. We use a function called longest common extension, and this can be solved in cubic time essentially. So let's continue. So let ti, n be the suffix of t starting at I. We're basically just defining a substring array of t, and then we are defining the LCE, where LCE I, j is the length of the longest common prefix of ti, n and tj, n, where tj, n is again another substring array of t starting at j, just like I is starting at I. So to give an example, LCE of Mississippi is LCE 3, 6. So I here is 3 and j here is 6. So we get 3 because the SSI is repeating at least twice. So to compute the LCE, we just need to match the characters one by one of the I to n substring array and j to n substring array until we get a mismatch. So this will obviously take linear time, but once you consider that we need to do all the LCE calculations, this will take cubic time. This method of doing it is inefficient, and again we can use our observation that when ti and tj are different, LCE I, j equals 0. But otherwise, LCE of I, j equals 1 plus LCE of I plus 1 and j plus 1. So essentially, LCE of I, j, if they are not different, you can just take it from the character and move on. So let's look at the linear time solution. First, the first step would be to sort all the suffixes lexicographically and add it to a suffix array. And then but before we go forward, we need to know how to construct a suffix array in linear time. So we use the DC3 algorithm for that. Just for example, on the right, you can see how the suffix array for banana is created. It's on the extreme right, it's organized lexicographically, and that is the suffix array that we need. So DC3 algorithm is pretty straightforward. It's sort of like a divide and conquer algorithm. You're splitting the string into triples and then recursively sorting it, sorting one half of it and then merging the other half based on the ranks of the half we sorted. And using this, we can get a sorted order of all the suffixes, and we can construct our suffix array. And this can be done in linear time. So the assumption is that to find the longest prefix, we need to compare only the consecutive suffixes in the array. The reasoning behind this is, since suffixes are sorted lexicographically, the longest common prefix must be present in consecutive ranks. So basically, since the consecutive suffixes in an array are generally to be sorted, they will generally have like the same common values in it, and it will be one or two ahead or behind. So it will be very easy to just find the repeating ones if we just check the consecutive ones of each suffix. So the last step would be to compute the LCE of consecutive pairs of suffixes and report the maximum value as the answer. But again, we need to know how to get the LCE of consecutive pairs. So far we looked at how to get the suffix array in linear time. Now we need to find out how we can get the LCE in a linear time. let's look at the Kasai's algorithm. So first we uh, inverse the suffix array and the suffix array that we obtained from the last step after doing the DC3 algorithm. So for each position in the original string, the suffix position is known in this sorted order. Iterate through the original string for each position and use the inverse suffix array to find the next suffix. So essentially we're just traversing through the original string and noting down the position using the inverse suffix array that we created. Using this, we can simply compute the LCE of the two adjacent suffixes in sorted order. So if the LCE of two adjacent suffixes is k, we can start the comparison at k minus 1 for the next pair of adjacent suffixes. This can be achieved because we know that they will share at least k minus 1 characters, which is a reasonable claim to make. So this solution again can be solved in linear time. And these are the references. Thank you.